Okay, everyone, welcome back. So today we're going to be reviewing for Exam 2 for Engineering 211 Statics at Stevens Institute of Technology. So on this exam, there's going to be two different types of problems. You're going to have trusses and frames, and I'm going to be doing 3 example problems. The first one being a truss and then 2 frames, and then we're going to go into identifying non-zero force members, whether to use method of sections, method of joints, and then with frames we're going to go into external reaction forces, internal reaction forces, and basically making sure that we answer all of the parts of the question. So like I said, we're going to be starting with a one second. So this is our first problem. Oh, this is not the problem I wanted. It's okay. Here we go. Okay, so this is our first problem, and it's basically saying that a roof truss is supported by a frictionless pin at A here, and a frictionless roller at I is loaded as should determine the forces in the members EG, HG, and JG, and indicate for each member whether it's in tension or compression, and list all zero force members. Okay, so let's just start by the first thing that I do when solving a truss problem is identify/solve for external reaction forces. So first we know that this is a pin, which means that this is going to have an upward AY and this is going to have an AX. This roller is going to only have a normal first perpendicular to where it's situated, so it's just going to have an IY going up. It's not going to have any horizontal force. And as we can see here, we know that AX, there's no, and we know that this is an equilibrium, so we already know that the F, the sum of forces in the X direction, is equal to 0. And there's no other forces in the 0 direction, so we know that AX is equal to 0. So then we're just left with solving for AY and IY. We know that this is symmetrically loaded in the sense that that this is a symmetric truss in the way that it's loaded. So what we can do is we're going to add up all of this loading, and you're going to get 1 plus 2 plus 2 plus 2 plus 1 is equal to 8 kilonewtons. We know that these two are the only reaction forces, so we know that this is an equilibrium, and we know that AY and IY are equal because of symmetric loading. And then because of that, we know that AY and IY are going to equal to 4 kilonewtons because they basically have to balance out this loading, and there's 2 of them, so we know that it's going to be 4 on this side and 4 on this side because this whole external reaction forces are in equilibrium. So we can say that AY is equal to 4 kilonewtons and IY is equal to 4 kilonewtons. Great. Now we can move on to identifying our internal reaction forces. And this is done either by method of joints, or a section. And typically it's done with a combination of both, but in this instance, we're going to start with a method of section, and we just got to keep in mind that when we do make our cut, it can only go through 3 trusses. And typically you want to make sure that those trusses are the trusses that you're solving for, so your unknowns. And then your third, that you want to make sure that the cut makes 2 separate sections. So in this instance, I'm going to make my cut because I can only do 3. I'm going to cut like this. Okay? And now we have a right and a left section. What I'm going to choose, which is what you want to choose as well, is you want to choose the section that has the least going on. So in this case, it's going to be the right section. So I'm going to redraw my cut, and I'm going to draw it over here. So we have J, I, this is G, we have how many? 1 kilonewton. This is 2.62 meters. We have a force here, I1. And then we know that this is like this. This is like that. And then we have this. I'm keeping in mind that we're solving for this and this. Okay. So, when you're solving for your internal reaction forces, we want to basically start with our moment. You always want to start either with a moment about a point, basically your 3 equations: moment, sum of forces in x direction, and sum of forces in y direction. So just looking at this, it doesn't seem that we have enough enough information to solve for our forces in x and y direction. So what I'm gonna do is, ideally you could take a moment about any point here, but I'm gonna choose point H because that will allow me to solve for f of GE. And you'll see. So I'm going to take the moment about point H in the positive direction, positive, is equal to. So the force of GH is not going to have a moment because it's in line with H, but f of G is going to have a negative moment, and you want to make sure you're taking the distance that's perpendicular. But in that case, we don't have that length, and since this is at an angle, we're gonna have to solve for that, which is gonna be, and it's not a net of 90, so what we're gonna have to use is basically the slope of this line. So I'm gonna go over here. We know that it's gonna be, what is 2 point, so we're gonna add all of these up. 2.4 plus 2.4, 2.4 times 4, we get 9.6. Basically, we're just going to do a slope like m, which is rise over run, which is delta y over delta x. You get 9.6 over 2.62. Actually, it's, what did we start at? We started at 2.6 minus 0.6. Let me move this. M is equal delta y delta x. So we're going to do y final minus initial, y final minus initial. So 2.62 minus 0.46. 9.6 divided by 2.16. This is not right. Hold up, give me 1 second. And my calculator is about to die. Oh, I messed this up. I flipped it. This is supposed to be on top. I apologize, ladies and gentlemen. this is supposed to be. And then we get 0.225, and basically think of our equation, y is equal to mx plus b, our typical slope equation. We're trying to find the distance 2.4 meters in, so like right here. So that's going to be 2.62 meters minus, 9.6 meters minus 2.4. We get 7.2, and we know the slope is 0.225, and you want 2 meters in. That's our slope. Which gives us 2.08 meters. Great. So that's our distance now here. That's 1 moment, because we needed this distance, which would have been perpendicular to h. Now then we're going to take the moment for I. I is going to have a positive moment, IY. And we look at that. Did we solve for IY? Yes, we did. So we're going to plug it in. We're going to have a distance that's perpendicular. That's going to be 2.4 meters. Then we're going to get, what's next? Then we're going to have to do the moment of FEG. We did FEG, FHG. Oh, and then we have to do the 1 kilonewton, this one. This one isn't going to have a moment because FHG, and it doesn't even concern us. So we're going to do 1 kilonewton. So that's going to have a negative moment. So negative 1 kilonewtons. The distance perpendicular is 2.4. Then we plug 4 in, kilonewtons, 2.4, because we previously solved for IY. And then we get F of GE is equal to positive 3.46. Great. Now, then we're going to look at, so we solved for that, and you know what we could just do? We're just looking for, what's it called? FGE. We also need to find this member as well. So let's do the method of joints. This is what I was talking about before, where you're going to basically want to do like a combination of a section and method of joints. So let's draw this member here. So we know F of GE is 3.46 kilonewtons. Then we know that, okay. And this is where we're going to look at the second part of the question. Let's look at, this is a non-zero force member. And the reason why this is a non-zero force member is because if you look at this joint over here, you have IY, and then you have JI, the force of JI. So these two cancel out, and there's nothing to cancel this out, so we know that this is a non-zero force member. So that doesn't even apply to our problem. So that actually solves our second part of our question, but we're going to revisit that later. So let's do the sum of forces. So we have the sum of forces in x direction, which we know is going to be 0. So f of x is equal to, we have this 3.46, and then we're going to need the component, x component of f, jg. Let's look at our drawing. We know this is 2.46. It is assumed that this one over here is 62 meters? 62 meters. So that means that calculation, the hypotenuse here is the square root of 2.46 squared plus 2.62 squared, and we need the x component, and that's going to be in a positive direction. So that means that that's going to be positive FJG is going to be this 2.46 over radical 2.46 squared plus 2.62 squared, and we get FJG is equal to 5.12 kilonewtons. Then now let's do in the y direction, which is FGH, and basically the same thing, except this is 2.6 square root of 2.46 squared plus 2.62 squared. Solve for this. We already did this. Plug this in. F of GH is equal to negative 3.79 kilonewtons. Fantastic. So now what we do is we look at our, we have to determine if they're in tension or in compression. So we solved for our unknowns, and typically a good rule of thumb is the way that you drew the diagram. So this is positive, this is going to be in tension, this is positive, this is going to be in tension, and when we write this, we're going to say FJH is equal to 3.79 kilonewtons in compression. You don't want to include your sign convention when you do write out your answers. Now, let's go back and try to identify non-zero force members. So we know that GI is a non-zero force member because it has a reaction force here, but there's no reaction force in the x direction. Now, let's look at this. We deleted this by accident earlier. We already said that AX is equal to 0, which means that there's no reaction force here. This is 0, so there's no force acting upon this, which means that AC is also a non-zero force member. So AC and GI are non-zero force members.